Hello and welcome back to the Hands on IT podcast. This month at Automox is Server Month, so I thought it'd be fun to dive into the history of servers. Now, personally, I love learning about the history of technology, so this podcast may be a little self-serving, but I think it'll be a lot of fun. Today, we're going to dig even deeper than normal, so we won't just talk about what happened. We'll explore the who, the key figures in server history, and the why behind their innovations. We'll discover and uncover the motivations, challenges, and rivalries that drove them, all set against the backdrop of tech and the society of its time, and how it shaped the technology of today. So grab a comfy seat, get some coffee, or whatever your energy drink of choice is, and let's journey through time from the age of room-sized mainframes to the era of cloud computing. So before we dive in to the history of servers, I always like to know where words come from. So I was telling my wife about writing this podcast, and she joked with me that server actually might be the oldest profession ever for, delivering food. And if you think about it, it's not too far off from what a server does in IT. Just swap out plates and food for data packets, and you're pretty much there. The roots of the computing term server go back to queuing theory, where mathematicians like Erlang in 1909 talked about operators. And then by 1953, Kindle's notation was calling the part of the system doing the work the server. So fast forward to the late 60s, and we have ARPANET, which is basically the internet's grandparent, where RFC5 labeled certain nodes server host to distinguish them from user hosts. The jargon file, which is a sort of hacker dictionary, later fleshed out that definition, describing a server as a process that does stuff for remote clients. Perhaps one of the most iconic early servers was the very first www server at CERN, set up by Tim Berners-Lee in 1990. It's still on display at CERN and still has a sign taped to it declaring, "This machine is a server, do not power down." Now, on to mainframe. A convenient way to think about it is, all mainframes are servers, but not all servers are mainframes. The term mainframe originally described these enormous central cabinets that housed the CPU and memory. In the 1950s and 60s, these beasts took up entire rooms. Big names like IBM led this charge, making machines that still run mission-critical tasks for banks, governments, and airlines today. Modern IBM Z systems are prime examples of mainframes. They can process massive volumes of data with near zero downtime. Meanwhile, a server can be anything from a cloud instance down to a little PC in your closet that's serving up movies to your living room. So while a mainframe absolutely counts as a server in the grand scheme of things, your average server, the one quietly humming away in a rack, doesn't have the scale, specialization, or the storied history to qualify as a mainframe. So let's start our story in the late 1950s and early 1960s. A time when computers were massive, expensive, and exclusive. So picture this. You walk into a computing center and see a room full of equipment with tall cabinets and blinking lights and spinning tape reels. These giants are mainframe computers, and at the center of this world is IBM, known fondly as Big Blue. Now, no one knows exactly where the nickname Big Blue originated, but it's widely believed to be a nod to IBM's corporate color scheme, the blue painted mainframes it produced, and its overwhelming dominance in computing. But before IBM became Big Blue, and long before the iconic blinking lights and spinning tape reels, computers were less glamorous and far more mechanical. Colossal calculating machines like the ENIAC and UNIVAC filled entire rooms using vacuum tubes by the thousands. Back then, computers weren't very common business tools yet. They were expensive scientific instruments funded mostly by governments for wartime code breaking or early atomic research. Visionaries like Alan Turing, John von Neumann, and Grace Hopper laid crucial groundwork for computing as we know it today. Alan Turing established core principles of computation and artificial intelligence. John von Neumann introduced the influential architecture that shaped nearly all subsequent computers. And Grace Hopper revolutionized software by developing early compilers in the widely adopted COBOL programming language, fundamentally changing how we interact with machines. It was Grace Hopper who famously coined the term debugging, literally removing a moth from a computer's circuits. But the arrival of IBM's mainframes in the late 50s and early 60s marked the pivotal transition from specialized calculators to powerful business machines. And that's where we'll start our story. To understand why servers are the way they are, we have to appreciate how IBM ruled the early computing world. Back then, IBM's philosophy was all about centralization and reliability. They provided the hardware, software, and support services as one comprehensive package to big companies and governments. This approach fostered intense client loyalty. If you bought an IBM mainframe, you were buying into an entire ecosystem, and switching to another brand was almost unthinkable. In society at this time, this era was marked by the space race and the Cold War, which meant governments were pouring money into computer research. Big businesses, too, were adopting computers to automate tasks. There was a saying that no one ever got fired for buying IBM. IBM was the safe bet, the gold standard of computing at the time. But IBM's dominance didn't just happen by chance. It was driven by figures like Thomas J. Watson Jr., the CEO of IBM in the 1960s, who had a bold vision. Under his leadership, IBM undertook one of the riskiest projects in tech history, the development of the System 360 mainframe family. The project was so large that it was often called the $5 billion gamble, a colossal sum in 1960 dollars. Now, Watson Jr. and his engineers, such as Chief Architect Gene Amdahl and project manager Fred Brooks, were motivated by a big idea: unifying IBM's computer line. Instead of separate machines, each with their own incompatible system, the System 360 series would share a common architecture and instruction set. This meant a program written for the smaller System 360 model could also run on a larger model, which was revolutionary at the time. It offered customers an upgrade path and protected their software investments. So imagine being an IT manager in 1965. Well, you likely may have been called something like an electronics data processing manager or something else. I digress. But anyways, your company has just installed a shiny new IBM System 360. It fills up an entire room, needs special cooling, and a team of operators in white lab coats to run it. But it's doing the work of what used to require dozens of clerks. In tech, this was the age of batch processing and time sharing. Multiple users on dumb terminals could run jobs on the same central machine. Essentially, the mainframe was the server for everyone's computing tasks. IBM's engineers faced huge challenges: how to make these systems reliable, because a crash could paralyze an entire company, and how to handle both business tasks like payroll calculation and scientific computations in one machine. The System 360 delivered, becoming a massive success and defining how servers were seen for years: big, centralized, and ultra-reliable. Now, what was happening outside of IBM at this time? The 1960s were a period of enormous tech optimism. The Apollo program was landing humans on the moon, largely thanks to IBM computers for guidance. At universities, researchers were experimenting with connecting computers together, the beginning of the ARPANET in 1969, which later became the internet. However, those academic projects were tiny compared to IBM's commercial might. Society was starting to see computers not just as mathematical instruments, but as business tools. Still, very few people had direct access to these machines. They were tucked away in corporations, universities, and government agencies. IBM's dominance wasn't accidental, though. Their computers powered the space race, Cold War defense systems, and corporate automations, leading to the famous saying, "No one ever got fired for buying IBM." Yet IBM faced competition both domestically and internationally. American competitors like Honeywell, Univac, and Control Data Corporation, or CDC, sought to disrupt IBM's dominance. Meanwhile, non-US companies such as Fujitsu and Hitachi from Japan, Bull from France, Siemens in Germany, and ICL and Ferranti from the UK also emerged as significant rivals. These companies tailored their systems to local markets, presenting viable alternatives to IBM's global dominance. But IBM had markets and minds. This is where our first philosophical divide in server history appears. IBM's approach was top-down: sell one big machine and have everyone share it. But some engineers and entrepreneurs started asking, does computing really have to be done on these giant, expensive machines? Can we make computers smaller and more affordable so that individual departments or labs might have their own? Enter the era of the minicomputer. So technology history often revolves around David versus Goliath narratives. A small, scrappy innovator taking on established giants. One fascinating twist is that frequently, after the underdog wins, they become the new giant themselves. This pattern is especially clear during the rise of minicomputers in the late 1960s and 70s. At this time, a new class of smaller computers emerged, minicomputers. Despite the name, they weren't tiny by today's standards. Imagine something roughly the size of a refrigerator or mini refrigerator. But compared to IBM's sprawling mainframes, these were indeed miniature. Leading this revolution was Digital Equipment Corporation, better known as DEC, co-founded by MIT engineer Ken Olsen. Olsen had a vision. Computing didn't need to rely solely on multi-million-dollar mainframes. Why couldn't smaller labs, universities, or departments have their own dedicated machines? In 1965, DEC introduced the PDP-8, widely recognized as the first commercially successful minicomputer. At about $18,000, it was a deal, and an affordable alternative to IBM's multi-million-dollar mainframes. It was roughly refrigerator-sized and manageable by a single department or lab. Suddenly, organizations could own their computers outright, dramatically shifting computing away from centralization towards more distributed departmental control. So why was this significant? The late 60s and early 70s marked a shift toward interactive computing. Time-sharing allowed multiple users to simultaneously interact with computers. Researchers wanted the freedom to experiment rather than wait for scheduled mainframe time on distant operators. The minicomputer perfectly fulfilled this desire. It was even a little bit culturally rebellious, a form of technological counterculture and a rejection to IBM's bureaucratic style. Imagine it's around 1970, young engineers at a university excitedly crowd around DEC's PDP-11 minicomputer. For the first time, they have their own machine directly accessible without bureaucratic hurdles. Malcolm Gladwell, in his book Outliers, famously highlights how Bill Gates benefited from this exact kind of unlimited access, gaining thousands of practice hours that contributed greatly to his later success. Back at IBM, executives were noticing DEC's impact. DEC captured IBM's traditionally ignored smaller companies and labs. This rivalry was more than commercial competition. It reflected contrasting philosophies. IBM championed brute force power, bundled services, and centralized control. DEC and Ken Olsen countered with simplicity, affordability, and accessibility. Ken Olsen famously, or perhaps infamously, said in 1977, "There is no reason anyone would want a computer in their home." Although frequently misunderstood, Olsen later clarified he envisioned centralized terminals rather than standalone home computers. His statement highlights the mindset of even the most innovative leaders at the time. They weren't dreaming of personal computing yet, just smaller servers that served whole groups. Ironically, Olsen's terminal in every home idea wasn't far from reality for today's tech enthusiasts. DEC's success, especially with the PDP-8, PDP-11, and later the VAX series, demonstrated that smaller, cheaper machines could succeed at serious computing tasks. DEC's engineering guru, Gordon Bell, pushed this vision even further with the VAX series in 1977, known as the Super Minis. For this project, Bell appointed a gifted software engineer named Dave Cutler to lead the development of the VMS operating system. But remember Cutler's name? He's going to show up a little bit later in our story with Microsoft. But anyway, the rivalry between DEC and IBM during the 70s drove innovation from both sides. IBM reacted by launching its own mini-computers, the IBM System 3, System 38, and later AS400, but both companies learned from each other. IBM became more agile while DEC scaled up to ensure reliability and capability. Now, while IBM and DEC engaged in commercial rivalry, another crucial development emerged quietly in the background. At AT&T Bell Labs, Ken Thompson and Dennis Ritchie created Unix in 1969, a lean, powerful, and highly portable operating system. Initially developed on a DEC PDP-7, Unix spread rapidly throughout universities by the late 70s, creating another philosophical split: proprietary, IBM's OS 360 and DEC's VMS, versus open, collaborative systems like Unix. To give a quick historical background, society faced economic uncertainty in the 1970s, with events like the oil crisis, but technology continued to advance. A new generation learned programming on minicomputers and Unix thanks partially to AT&T's unusual licensing approach. Due to antitrust restrictions from earlier lawsuits, AT&T couldn't commercialize Unix traditionally, so they licensed it cheaply to academic institutions. Universities like UC Berkeley flourished under this open environment, producing influential Unix variants such as BSD. Only in the mid 1980s, after antitrust rulings changed, did Unix fragment into numerous proprietary variants. IBM's AIX, Sun Solaris, HP's HPUX, and DEC's Ultrix. Nevertheless, the earlier open approach to Unix seeded principles of collaboration and openness, directly influencing the later Linux movement. By the end of the 1970s, we've arrived at a fascinating crossroads. IBM's centralized mainframe legacy, DEC's decentralized minicomputer philosophy, and Unix open collaborative ethos. Hold on to these ideas, because another computing revolution was just around the corner, one that would put technology directly into the hands of individuals and disrupt computing forever. The rise of the personal computer. Okay, now it's the late 1970s. For hobbyists or small businesses, a DEC minicomputer was often too costly. However, advances in microprocessor technology, small, affordable CPUs like Intel's 8080 and the MOS 6502, spawned a new generation of microcomputers. And around 1977, the Apple II, Tandy TRS-80, and Commodore PET emerged, launching the personal computing revolution. Initially, these weren't really server-ready machines, but tools for enthusiasts or simple office tasks, yet they laid the groundwork for a seismic shift in computing. Enter Bill Gates and Microsoft's vision. Bill Gates, alongside childhood friend Paul Allen, envisioned a computer on every desk and in every home. Motivated by this idea, Gates and Allen founded Microsoft in 1975, initially writing basic interpreters for these early microcomputers. Their turning point, and one that would redefine the computing industry, arrived in 1980 with IBM's entry into the market. IBM, who at the time was the undisputed giant of computing, saw the PC revolution coming, but they were woefully unprepared. In 1980, their engineers were scrambling to build an operating system, but instead of developing one in-house, they looked to outside vendors. In a fascinating twist, Gates initially directed IBM to Digital Research, whose CP/M was the standard for microcomputer operating systems. CP/M was created by Gary Kildall, and he pioneered user-friendly features such as directory file structures and command line utilities. However, a fateful miscommunication occurred. Gary Kildall was either absent, flying his plane according to popular lore, or stalled over negotiations on non-disclosure agreements. This misstep radically altered the industry's trajectory. Desperate for an operating system, IBM returned to Microsoft. Bill Gates sensed a golden opportunity, even though he didn't even have an operating system at the time. Gates and Paul Allen seized this chance, and rather than creating an operating system from scratch, they quickly acquired a rudimentary 16-bit system called QDOS, or Quick and Dirty Operating System, from Seattle Computer Products. Now, this was a temporary solution initially developed by Tim Patterson. They bought this for roughly $50,000, and Microsoft obtained non-exclusive rights, refined the operating system, and rebranded it as MS-DOS, and licensed it to IBM. The true genius of Microsoft's deal was this. IBM paid just approximately $430,000 for DOS and some programming languages, but crucially, Microsoft retained rights to license DOS to other computer manufacturers. IBM had inadvertently established the IBM PC architecture as a market standard, which competitors quickly copied. However, Microsoft, not IBM, controlled the operating system. Throughout the 1980s, PC clone manufacturers like Compaq, Dell, and HP eagerly manufactured IBM-compatible computers, and every one of these machines needed MS-DOS. IBM treated software as just another hardware component, failing to realize that software, not hardware, would define the future. Bill Gates, however, saw clearly that whoever controlled the operating system would control the market. Now, by the mid-1980s, IBM's dominance over personal computing waned, while Microsoft soared. Now, initially, MS-DOS wasn't really suited for server use. It was single-user and single-tasking, and it couldn't compete with Unix mainframes. However, Microsoft's dominance in the PC market laid the foundation for its eventual expansion into server technology. The company believed that the same philosophy that had made computing affordable and accessible could revolutionize enterprise computing as well. This vision took shape with Windows NT, a project that required an experienced architect to bring it to life. Enter Dave Cutler. Frustrated by DEC's decision to cancel his Prism project, his ambitious next-generation operating system, Cutler saw Microsoft as a fresh opportunity to build something groundbreaking with a team he trusted. Gates and Ballmer, eager to bolster Microsoft's enterprise capabilities, offered him the resources and autonomy to develop a modern operating system from the ground up. To further entice him, they not only provided a competitive financial package, but also agreed to hire several of his key engineers from DEC, ensuring that he had the support of a team already aligned with his vision. Ultimately, the chance to shape the future of computing on his own terms proved irresistible. In 1988, Cutler joined Microsoft, where he would go on to lead the development of Windows NT, a foundational pillar of modern enterprise computing. Meanwhile, DEC, who was once a powerhouse in mini computing, struggled to adapt as the industry shifted towards affordable, standardized personal computers and commodity hardware. Its high-quality but expensive mini computers lost ground to more flexible, lower-cost PC-based solutions. Internal projects like Prism intended to reinvigorate DEC's competitive edge, but they were ultimately scrapped, prompting key engineers like Dave Cutler to leave. Over time, DEC's decline became irreversible, culminating in its acquisition by Compaq in 1998. And 4 years later, Compaq itself was absorbed into Hewlett-Packard, marking the end of DEC as an independent entity. However, its legacy lived on, influencing modern computing through its innovations, ideas, and migration of its talent. Most notably, Dave Cutler's role in shaping the future of Microsoft's enterprise ambitions. IBM and Microsoft. So collaboration and conflict, which is a theme we will see throughout this story. IBM recognized that the PC needed a robust operating system to support heavier business applications. They partnered with Microsoft in the mid-1980s to create OS2. Initially optimistic, the partnership aimed to harness powerful Intel processors such as the 8286 and 386 and mainframe-inspired reliability. OS2's 1987 release featured advanced capabilities such as protected memory and multitasking, but the two companies soon found their goals diverging sharply. By 1990, Windows 3.0's overwhelming popularity convinced Microsoft that their future lay with Windows, not OS2. Disagreements intensified. IBM, committed to reliability and backward compatibility, was slow-moving. Microsoft sought rapid development and broader hardware compatibility. By the early 1990s, their partnership fractured completely. And in the early 1990s, enterprise computing was ruled by proprietary Unix operating systems from companies like Sun Microsystems, IBM, HP, and Silicon Graphics. Now, each of these offered their own Unix flavors, and they ran on specialized hardware, meaning that each vendor's system was largely incompatible with other vendors. These powerful Unix servers and workstations formed the backbone of corporate IT, from banking to aerospace. Sun Microsystems in particular exemplified this era. Co-founded by Scott McNealy, Sun produced Spark-based servers running Sun's Solaris Unix. The company's ethos was championed by early employee John Gage and was encapsulated in the famous slogan, "The network is the computer," a vision of distributed computing that presaged cloud concepts. In practice, this meant that Sun's systems were built with networking in mind. They pioneered technologies like NFS file sharing, and high-end Unix servers of the day were expensive and immense. A top-of-the-line Sun Starfire E10000 would cost over $1 million and filled multiple racks. Scott McNealy was a vocal proponent of open networking, and under his leadership, Sun's workstation culture thrived. Meanwhile, John Gage's mantra about the network being the computer signaled an understanding that computing power in the enterprise would increasingly be a shared network resource rather than isolated boxes. So with Unix, the ecosystem was controlled by a handful of vendors until a very disruptive newcomer emerged from an unlikely place. Enter 1991 and the birth of Linux, Linus Torvalds' hobby operating system. In August of 1991, a 21-year-old Finnish computer science student named Linus Torvalds announced on the Usenet forum comp.os.minix that he was working on a new and free operating system kernel as a hobby. He modestly noted, "I'm doing a free operating system, just a hobby, won't be big and professional like GNU," referring to the GNU project's efforts to build a free Unix-like operating system. At the time, this message didn't make waves beyond hobbyist circles, yet Torvalds' project, which he named Linux, would fundamentally reshape server technology in the coming decades. Now, what made Linux different from the proprietary Unix systems was its development model. Torvalds released Linux under an open source license, initially his own, then switching to the GNU GPL in 1992, inviting anyone to use, study, modify, and share it. Developers around the world jumped in to contribute code and improvements, and this was a collaborative effort from day one, a stark contrast to the closed, corporate-controlled Unixes. By the 1990s, Linux had grown into a stable kernel, and volunteer developers had created all the missing pieces of a full operating system by combining Linux with GNU software. Linux distributions began to emerge and packaged the kernel and software into easy-to-install systems. 1993 saw the birth of Slackware by Patrick Volkerding and Debian, founded by Ian Murdoch, and these are two of the oldest surviving Linux distributions. In 1994, Red Hat was founded by Bob Young and Mark Ewing, and by 1995, Red Hat Linux was released commercially. Each distribution had a community of maintainers and users that contributed to its improvements. This proliferation of Linux distributions meant that anyone could get a Unix-like operating system on inexpensive Intel PCs, undermining the need for costly proprietary Unix workstations. As Sun's Bill Joy later observed, Linux completely undermined the software license business of the Unix vendors. Linus Torvalds had become the leader of a global development community with Linux. He set the tone with a pragmatic, collaborative approach, accepting contributions on their technical merit. This attracted quality improvements from thousands of programmers. One internal Microsoft memo in 1998 even noted that the ability of the OSS process to collect and harness the collective IQ of thousands as something simply amazing. In other words, the open and collaborative style of Linux development enabled it to improve at a pace no single company can match. Torvalds himself later reflected that the success of Linux was due to many people. "I'm basically a coordinator," he said, "and the code has moved far beyond my own skills," a testament to the power of open collaboration. By the late 90s, Linux was no longer a student's hobby operating system. It was a robust, Unix-like system running on everything from personal computers to server hardware. Still, Linux had not yet been fully embraced by industry, and that changed as influential companies began to see the potential of this communal project. So IBM, Big Blue, they made a big bet on Linux and the changing landscape. As Linux gained reliability, IBM took notice. Under CEO Lou Gerstner, IBM, in 1999 through 2000, decided to make a monumental commitment to Linux. In 2000, Gerstner announced IBM would spend $1 billion on Linux development and support in the next year. This was a shocking validation of open source. IBM began porting its enterprise software to Linux and even adapted Linux to run on IBM mainframes. Gerstner's rationale was that IBM was convinced that Linux could make computing easier and free from proprietary operating systems. In other words, IBM saw Linux as the logical successor to Unix, a vendor-neutral platform that it could help optimize for all its hardware. This strategic shift by a tech giant gave Linux enormous credibility in corporate circles. Microsoft, on the other hand, was not happy with Linux. They feared open source software, and it set off a bunch of alarms. Microsoft had been pushing its own server operating system, Windows NT, throughout the 90s as a competitor to Unix. By the late 90s, Windows NT and its successor, Windows 2000, were starting to power some enterprise servers, especially for file sharing and applications on cheaper x86 hardware. But Microsoft viewed Linux as a serious long-term threat to its Windows Server business. In 1998, a series of leaked internal memos dubbed the Halloween documents revealed Microsoft's concerns that Linux and the open source movement could erode Microsoft's market. The memo frankly stated that free software like Linux was a potential serious threat to Microsoft, and that it had achieved quality that can meet or exceed commercial software that Microsoft was producing. Microsoft executives acknowledged Linux as a long-term credible challenge and noted that traditional FUD, or fear, uncertainty, and doubt tactics wouldn't work against a decentralized open community system. Now, by 2001, Microsoft's then CEO Steve Ballmer went so far as to call Linux a cancer that attaches itself to everything it touches, an indication of just how disruptive Linux appeared to be to the established proprietary model. About 14 years later, Microsoft's stance would do a complete 180. The late 90s were turbulent for the traditional Unix vendors. Some, like Sun Microsystems, doubled down on their own software, and their CEO, Steve McNeely, went as far to say open source really means no revenue. Others, like SGI and HP, eventually decided to support Linux on their hardware, in addition to their proprietary operating systems. IBM, as noted, went all in on Linux across its product lines. This era saw a mingling of old and new. IBM selling mainframes running Linux, Dell shipping PCs with Linux, and Oracle and other enterprise software available on Linux. The landscape was shifting from many incompatible Unix variants towards an open standard platform, Linux, that anyone could run on commodity hardware. In short, by the year 2000, computing advancements were clearly becoming a collaborative effort. The senior IBM executive at the time, Irving Lansky-Berger, spearheading IBM's Linux initiative, said, "Linux is the result of a global community coming together. It's not any one company," highlighting that cooperation was the new catalyst for innovation. The stage was set for open source software, with Linux at the forefront, to enter the enterprise mainstream in the 2000s. All right, now it is the turn of the century. We have reached the year 2000. The 2000s saw Linux transform from an upstart to a core part of enterprise IT. Companies like Red Hat led the way in commercializing Linux while keeping it open, and Red Hat shifted in 2002 from offering a free hobbyist OS to a subscription-based enterprise platform called Red Hat Enterprise Linux, or RHEL. With RHEL, Red Hat provided businesses with a stable, supported Linux distribution, a model that proved incredibly successful. By mid-decade, Red Hat became the first billion-dollar open-source company. Fortune 500 firms began migrating expensive Unix systems to Linux running on x86 servers. IBM's $1 billion investment in global support of Linux paid off as many IBM customers chose Linux on IBM power servers and mainframes. Now, other major IT vendors such as HP, Dell, and Oracle also embraced Linux for their enterprise offerings. In 2003, HP's CEO Carly Fiorina said, "Linux has entered the mainstream," as HP reported selling billions in Linux-based hardware and services. In parallel, open source software beyond Linux was flourishing. The early 2000s saw the rise of the LAMP stack, which stood for Linux, Apache, MySQL, and PHP, Perl, and Python, as the dominant platform for web servers and applications. This entirely open source stack powered a huge portion of the World Wide Web. The Apache HTTP server in particular was a cornerstone. It became the most popular web server software, running on an estimated 2/3 of websites at one point. The combination of Linux, Apache web server, MySQL databases, and PHP scripts enabled developers to build dynamic sites at a low cost. A large part of the internet was being provided with open source software. In other words, open source tools made building websites accessible to everyone and fueled the dot-com boom. Famous platforms like Wikipedia, Facebook, and WordPress all launched on LAMP stack foundations. The collaborative nature of these projects was key. Apache was developed by a community, the Apache Group, and showed how open source could produce rock-solid infrastructure. MySQL, created by David Montewiedenes and David Axmark, was a free database that undercut proprietary databases in many web use cases. PHP, started by Rasmus Lerdoff, similarly grew via contributions from developers worldwide. Each component had its own set of contributors, but using them together created a powerful synergy. Major tech companies that emerged in the 2000s, such as Google, Amazon, and Facebook, all built their product on top of open source operating systems and tools internally, even if they didn't always publicize it at first. For example, Google, from its beginnings in 1998, ran on Linux servers. Amazon migrated its infrastructure from proprietary operating systems to Linux around 2000 to cut costs and improve scalability. Now, by the mid-2000s, even former skeptics were embracing open source. In 2001, Microsoft's CEO had derided Linux. By 2005 and 2006, Microsoft started quietly working with open source, releasing PHP on Windows, contributing to Apache. IBM's massive advertising campaign, Peace, Love, and Linux, in 2001, plastered Tux, who is the Linux Penguin mascot, on billboards signaling that open source had arrived. And in 2008, IBM, Intel, and HP and other industry leaders formed the Linux Foundation to collaboratively support kernel development. The telling milestone came in 2008 when Google released Android, a Linux-based mobile operating system, as open source, putting Linux into billions of phones. Open source operating systems were no longer on the fringe. It was the default for new systems. Microsoft's own turnaround culminated in 2014 when the CEO Satya Nadella declared on stage that Microsoft loves Linux, even displaying the message on a slide. This was the ultimate acknowledgement that the collaborative open model had prevailed. By the late 2000s, the server world had broadly shifted. Instead of proprietary Unix on specialized hardware, companies large and small were overwhelmingly deploying Linux on commodity x86 servers, running open source web software. Proprietary Unix shipments such as Solaris, HP, and AIX were in decline year over year. A Gartner report in 2008 showed Linux servers had surpassed Unix servers in unit sales. The collective innovation of thousands of developers had given IT departments a gift, a stable, high-performance operating system, essentially for free, aside from optional support contracts with no vendor lock-in. Yet, even as software became more flexible and shareable, physical servers were still physical, one server, one operating system instance. That paradigm was about to change with the next big leap, virtualization. Virtualization is the technology that lets one physical server host multiple virtual servers, each with its own operating environment. While the concept existed on IBM mainframes for decades, IBM's VM operating system in the 1970s virtualized mainframe hardware, it wasn't until the 2000s that virtualization hit mainstream x86 servers and data centers. This revolution was spearheaded by a startup called VMware, co-founded in 1998 by Diane Green and a team of computer scientists. VMware introduced software, a hypervisor that could emulate a complete hardware environment and software, allowing multiple operating systems to run on one machine. In 1999, VMware launched VMware Workstation for desktops, and in 2001, it released VMware ESX Server, the first hypervisor for enterprise servers. The effect of virtualization on server technology was dramatic. Before virtualization, companies often ran one application per physical server to ensure reliability, leading to low utilization. Many servers were vastly underused, sitting idle but consuming power and space. Virtualization changed that by consolidating workloads. A single powerful server could run, say, 10 virtual servers, replacing 10 physical boxes. This drove efficiency way up. By decoupling software from hardware, it also made infrastructure far more flexible. Need a new server for an application? Instead of buying a new machine, IT admins could spin up a new virtual machine on an existing host in minutes. The early adopters saw huge savings. For example, some reports say that by 2005, many enterprise data centers achieved consolidation ratios of 5-to-1 or even 10-to-1, meaning that one server did the work formerly done by many. By 2009, a report by IDC estimated that 18% of all new servers shipped were virtualized, running hypervisors like VMware, a number that would only grow in the following years. Virtualized at first became a common IT policy. Companies like IBM and HP also offered their own virtualization solutions. In open source, hypervisors like Xen and KVM emerged mid-decade as well. But VMware remained the market leader, thanks in part to Diane Green's technical and business leadership in its early years. So Diane Green really deserves mention here as a key figure, VMware CEO. She evangelized the radical idea of software-defined servers. Under her tenure, VMware's tech became ubiquitous in data centers. It wasn't just proprietary, though. Academia and open source It wasn't just proprietary efforts, though. Academia and open source contributors developed the Xen hypervisor starting at Cambridge and the KVM module for Linux, both open source alternatives that gained adoption. Xen was used by Amazon for its early cloud, and KVM became part of Linux. Again, we see collaborative advancements here. While VMware was a private company's product, the concepts and innovations in virtualization were shared across the industry through conferences and papers. The result was a fast maturation of virtualization technology. By the end of the 2000s, virtualization had fundamentally changed server management. Servers were now files. You could create, copy, and migrate VMs like data. This set the stage for the next evolution, treating infrastructure itself as an on-demand service, which is the essence of cloud computing. In 2006, the industry took a leap forward that fully embraced the idea of computing as a shared utility. Amazon Web Services, or AWS, Amazon's new tech arm led by Andy Jassy under Amazon CEO Jeff Bezos, introduced two new landmark services. Amazon S3, which is simple storage service, in March 2006 for online data storage, and Amazon EC2, or Elastic Cloud Compute, in August of 2006 for running virtual servers on demand. With AWS, Amazon essentially opened its own data center infrastructure for others to use on a pay-as-you-go basis. No longer did you need to buy and maintain your own servers. You could provision servers in the cloud remotely using Amazon's massive data centers and pay only for the hours you use. Bezos was a key visionary here. He famously compared AWS to the electric grid, saying in the early 1900s, businesses generated their own electricity on premises until centralized utilities took over. Bezos asks, why should companies in 2006 have to build their own data centers when they could just plug it into a cloud? AWS was born from that idea, and initially many were skeptical. Renting compute power over the internet sounded fanciful to some IT veterans, but it caught on quickly, especially with startups and forward-thinking teams. Notably, AWS's cloud was built on Xen virtualization and ran on Linux. The open source technologies of the prior era were the new underpinning. Amazon didn't have to invent a new operating system or hypervisor. It leveraged Linux and Xen and contributed improvements back to those communities as well. So the cloud innovation was as much about business model as technology. The tech, commodity servers, virtualization, and broadband internet had matured to the point where AWS could orchestrate it into a service. The availability of on-demand infrastructure was revolutionary. Need a server for a day, a week? With AWS EC2, you could rent it, use it for 24 hours, and then shut it down. No hardware to buy, no strings attached. This dramatically lowered the barrier of entry for new online services and experiments. The developer with a credit card could launch an app accessible worldwide without owning a single server. By 2010, AWS had hundreds of thousands of customers, and the concept of cloud computing had firmly entered the mainstream of IT. Other tech giants responded. Google launched its Google App Engine in 2008 and later Google Compute Engine. Microsoft rolled out Azure in 2010, initially focused on Windows, but soon supporting Linux as well. Even traditional hardware makers tried to offer cloud or utility computing services with limited success. The lesson was clear. Computing was becoming centralized and service-oriented again, much like the mainframe timeshare days, but now with open standards and the scale of the internet. In the enterprise, cloud adoption initially raised fears, security, control, so the hybrid cloud approach became common. Companies kept some servers in-house and put others on AWS or Azure. Over time, as trust grew, even large financial and government institutions started using public cloud for portions of their workload. Now, Jeff Bezos, obviously a key figure here for greenlighting AWS, reportedly after an executive retreat in 2003, strategizing on how to leverage their massive infrastructure and expertise. Andy Jassy, who was often credited as the father of AWS, drove the business execution and evangelism, convincing companies to try this new model. They, along with the engineers who helped build EC2, many of whom came from the open source world, collectively changed how servers are perceived, no longer as a physical asset you own, but as a capacity you can acquire as needed. This is a deeply collaborative model, massive shared data centers serving millions of users and businesses. From a technology standpoint, the cloud is an outgrowth of everything earlier. Commodity Linux servers running hypervisors, managed by automation software distributed across the globe. It's the ultimate expression of the network is the computer. In fact, Sun's old motto found new life in the cloud era. A 2018 Cloudflare blog even explicitly referenced it, saying the network is the computer is finally reality in cloud computing. Now, by the early 2010s, the prevailing trend was clear. Whether via public cloud providers or private clouds using similar technology, organizations treated servers as flexible pools of resources. This enabled another wave of innovation at the application architecture level, which came to fruition with containers. Around 2013, a new technology paradigm emerged from the open source world: containerization. Containers are a lighter weight form of virtualization, and instead of emulating an entire machine like VMs do, containers isolate applications using features of the operating system kernel like namespace and control groups in Linux. This allows many isolated applications to run on the same operating system with much less overhead than full virtual machines. Now, while concepts like this have existed in Unix and Linux for years, such as BSD jails or LXCs, it was a tool called Docker that really made containers accessible and popular. In March of 2013, Solomon Hykes and his team open sourced Docker. Docker provided an easy way for developers to package their apps into portable containers and run them anywhere. Docker's clever use of high-level APIs and simple commands meant developers could define a container image with all the libraries their app needed, and then instantiate containers from it in seconds. This solved the classic "it works on my machine" problem. If it runs in a Docker container, it will run the same way on any Linux server with Docker. So Solomon Hykes, Docker's founder, is a key figure here. He often credits the wider community for Docker's rapid development, and once open sourced, Docker gained contributors from major companies and individual developers alike. Within a year, tech giants like Red Hat, IBM, Google, and Microsoft were all deeply investing in Docker's ecosystem. It was open source collaboration at work. Each saw the benefits of standardizing container technology. Docker's success also rested on existing pieces contributed by Google and others in the Linux kernel, again highlighting how communal groundwork enabled new innovation. By 2014, Docker had millions of downloads. Containers coincided and enabled the rise of microservices, an architectural style where applications are split into many small single-purpose services that can be developed and deployed independently. Docker made microservices practical because each service could run in its own container with minimal footprint. Companies like Netflix and Amazon, already moving toward microservices in the early 2010s, eagerly embraced container technology to deploy these services more efficiently. The culture of DevOps, developers and operations collaborating, also helped. Infrastructure as code, continuous integration, continuous deployment, all these practices meshed well with containerization. As organizations deployed hundreds or thousands of containers, a new challenge arose. How can we coordinate and manage all these containerized applications across clusters of servers? Google, which had long used an internal system called Borg to schedule workloads in its data centers, recognized this need. In 2014, Google introduced Kubernetes as an open source project to orchestrate containers. It was originally created by Google engineers Brendan Burns, Joe Betta, and Craig McLuckie, and Google donated it to the community, eventually to a new Linux Foundation organization, CNCF, and Google open sourced it. Kubernetes automated the deployment, networking, scaling, and management of containers across clusters. In effect, Kubernetes turned a pool of servers into a single large computer for containers. So you can declare the desired state, example, running 10 copies of this container, ensure one per node, etc., and Kubernetes can handle the rest. Kubernetes quickly became the de facto standard for container organization, backed by a broad coalition, including Google, Red Hat, IBM, and many others. They all contributed to it. By 2017, Kubernetes was one of the fastest growing open source projects ever, with over 700 contributing companies, and outpacing alternatives like Docker's own Swarm and Apache Mesos. This was a remarkable example of competitors collaborating. All of the cloud providers and enterprise vendors worked on Kubernetes since none of them wanted to be left behind. The result was that by the late 2010s, whether you were on AWS, Azure, Google Cloud, or on-premise, Kubernetes was a common layer. The container revolution brought about a fundamental change in how we build and run software. Applications became more modular, updates more frequent, and environments more uniform. Teams could adopt a cloud-native approach, designing systems explicitly for scalability and resilience on cloud infrastructure, often using containers and Kubernetes. So, looking at this era, it is striking at how much this era exemplifies collaborative development. Docker's open source project ignited containerization, and Google's open sourcing of Kubernetes then united the industry. None of this would have happened, or at least not this fast, in a closed source world. By the end of the 2010s, a developer could write code, package it in a Docker container, and deploy it to a Kubernetes cluster running on any cloud or any data center, and it would just work. That portability and efficiency is a direct result of community-driven standards. As the 2010s drew to a close, the influence of open source software and server technology was unquestionable. Two major acquisitions in 2018 underscored this. IBM's $34 billion purchase of Red Hat and Microsoft's $7.5 billion purchase of GitHub. IBM's Red Hat deal, announced in October of 2018, was the largest software acquisition ever at the time. It was a full circle moment too. IBM, which had helped validate Linux 18 years earlier, was now investing tens of billions in the leading Linux and open source enterprise company. Gianni Rometty stated that the move would make IBM the number one hybrid cloud provider, combining IBM's enterprise reach with Red Hat's open source expertise. Red Hat's flagship product was RHEL, and still is, a staple of data centers worldwide. And its OpenShift platform, a Kubernetes-based platform as a service, was a leader for hybrid cloud deployments. By acquiring Red Hat, IBM signaled that the future of servers was hybrid cloud, blending on-prem and cloud, all built on open source foundations. It also proved how valuable open source companies could be. Even though their code is freely available, the value was in their collaborative development model and the trust they'd earned in the community. Meanwhile, Microsoft, once the archenemy of Linux, had undergone a remarkable transformation under Satya Nadella. Nothing symbolized this more than Microsoft acquiring GitHub in 2018. GitHub is the largest repository of open source code, a platform where over 28 million developers share and collaborate on projects. By buying GitHub, Microsoft essentially became a steward of the open source development process itself. This would have been unthinkable in the Steve Ballmer era, but Satya Nadella's Microsoft explicitly embraced developers' freedom. Microsoft even hosts its own code on GitHub, including famously open sourcing .NET and Visual Studio Code, and later even the Windows calculator. The GitHub acquisition confirmed that open source collaboration was now a cornerstone of the software industry, so much so that one of the world's biggest companies was willing to pay billions to be part of the ecosystem. The late 2010s were defined by a move to hybrid cloud and multi-cloud deployments. Enterprises realized that they wanted the agility of the cloud, but also needed to integrate with on-prem systems and avoid too much lock-in with any single cloud provider. Tools like Kubernetes made it easier to span environments, run some containers on AWS, some on your own servers, some in Azure. With open source software running everywhere, major cloud players began investing heavily in open source projects, sometimes to the point of acquiring companies like Red Hat and IBM. It was that the late 2010s were a period of consolidation, larger firms scooping up open source startups, ensuring they had a stake in the communities driving the server technology forward. Some open source maintainers worried about corporate influence, but overall the result was more resources poured into the project. Perhaps the best measure of how far things have come was by 2019, Microsoft, the same company whose executives once likened open source to cancer, had become one of the biggest contributors to open source projects. In fact, Microsoft was the single largest contributor to Kubernetes by some accounts, and on GitHub, Microsoft employees contributed to thousands of projects. This cultural shift was encapsulated in Satya Nadella's famous mantra, Microsoft loves Linux, which by 2015 he was literally displaying on stage. It was more than a slogan, though. By 2018, over half of the workloads on Microsoft's Azure cloud were Linux-based. In a poetic turn of events, the dominance of Linux and open source tech forced even proprietary giants to collaborate and adapt. In summary, the late 2010s cemented an understanding that progress in server technology, from operating systems to cloud platforms, is a collaborative endeavor. No single company could realistically build and maintain all the complex pieces alone. Open source communities, often backed by multiple corporations, drove innovations. Servers became even more of a commodity in some ways. You can run interchangeable containerized workloads on any cloud, but also more specialized in other ways, tailoring to specific environment needs, which leads us to our final theme, specialization for new workloads like AI. So we're in the 2020s now, and a new force has begun to dominate data center discussions: artificial intelligence and machine learning workloads. Training advanced machine learning models like deep neural networks for image recognition or language processing requires immense computing power, and it's quite different from traditional web and database workloads. This shifted attention to accelerator hardware, especially GPUs. Companies like NVIDIA, known for their graphics cards, suddenly found their chips in high demand for AI training and servers. Over the latter half of the 2010s, NVIDIA positioned its data center GPUs, Tesla and the later A100 and H100 models, as the go-to solution for AI computations. By 2023, NVIDIA was estimated to control around 80% of the AI accelerator market, essentially dominating the supply of AI-focused server hardware. The collaborative angle here is that much of the AI research driving this boom was shared openly. Google's TensorFlow framework was open sourced in 2015, and Facebook's PyTorch soon after, which accelerated AI adoption and in turn demand for GPU-heavy infrastructure. Data centers started to look different, racks filled with not just CPUs and RAM, but with GPU cards drawing heavy power. The definition of a server expanded. Was a server a single CPU box or a multi-GPU system, or even an entire pod of graphics cards? Traditional x86 CPU makers like Intel and AMD scrambled to catch up in AI accelerators. Intel acquired AI chip startups, and AMD invested in its Radeon GPU line for compute, but NVIDIA still had the lead, thanks in part to its CUDA software ecosystem, which had grown with input from developers since the 2000s. In an ironic twist, some supercomputers and cloud providers began to refer to GPU-heavy boxes as servers and the CPU as just a coordinator. The balance of power in computing is starting to shift again. Accelerators are now first-class citizens. Another trend in the 2020s is the rise of custom silicon in servers. Cloud providers, to optimize for performance and cost, started designing their own chips. For example, Amazon developed the Graviton series of ARM-based CPU processors for its EC2 cloud servers. The first Graviton, which came out in 2018, was rather modest, but Graviton 2 and Graviton 3 delivered competitive performance with significant cost and power advantages. By 2024, over 90% of Amazon's biggest EC2 cloud instances were using Graviton-powered instances for some of their workload. That's a remarkable validation of an open instruction set, architecture, ARM, and of customization. Amazon tailored Graviton to its needs with help from the ARM ecosystem and Annapurna Labs, an acquired startup. Google similarly designed TPUs, or tensor processing units, custom ASICs, specifically for machine learning tasks, which it first deployed internally around 2016 and later offered via Google Cloud. Other cloud providers followed suit. Microsoft is working on FPGA-based AI accelerators. Alibaba and Tencent are designing chips for their clouds. Even beyond cloud providers, the whole industry saw ARM processors finally breaking into the server room. In 2022, ARM-based CPUs from companies like Ampere and Fujitsu began showing up in on-premise servers and supercomputers. Forecasts predict that ARM could reach 20% of server shipments by the middle of the decade, eroding Intel's long-held dominance. The ARM ecosystem allows many companies to contribute to different designs and by the need to optimize for new workloads and power efficiency. Notably, the world's fastest supercomputer in 2021, Japan's Fugaku, runs on ARM-based processors as a result of development between Riken and Fujitsu with open collaborations on certain aspects. Another aspect of the 2020s server evolution is the extension of the cloud to the edge, deploying servers closer to the end user for lower latency applications like IoT, autonomous vehicles, or augmented and virtual reality. Finally, it's worth noting how AI and open source intersect. Much of the software used in AI training, like TensorFlow, PyTorch, Kubernetes itself for scaling AI jobs, is open source. Even some state-of-the-art models are released openly on platforms like Hugging Face. This has led to a flourishing AI research community that builds on shared work, which in turn drives more demand for computing. It's a virtuous cycle. Open collaboration in software creates breakthroughs that require new hardware that pushes the industry to innovate in servers, and those innovations get disseminated, NVIDIA, the cycle of collaboration continues at the bleeding edge. Today's servers Today's servers in the cutting edge data centers might have exotic components like GPUs with 80 gigabytes of memory or more, specialized neural processing units, racks with cooling for 400-watt GPUs, but they are managed and accessed in the same open frameworks developed over the past 2 decades. A container of an AI training job can run on a cluster of GPU servers in Azure or on a private supercomputer in a lab. Either way, it's likely orchestrated by Kubernetes and running on Linux. The consistency and flexibility achieved is astounding. And if one thing is clear, it's that none of this would exist without cumulative cooperative efforts of thousands of engineers, researchers, and companies contributing to the global knowledge pool. Server technology has advanced through a series of interconnected phases, each building on the innovations and lessons of the previous. So we end our story in an era where open collaboration is the norm, from the operating systems to cloud management to application frameworks. The most important server technologies are developed in the open, with contributions from individuals, communities, and companies large and small around the world. A recurring theme has been the network is the computer. What started out as a bold slogan at Sun Microsystems in the late 80s became reality in the age of cloud computing and globally distributed systems. Servers today are not isolated boxes. They are part of a vast fabric of interconnected compute and storage, accessible on demand. This has only been possible because of standardization, largely through open source software and cooperation across the community. When Brendan Burns, one of Kubernetes creators, reflected on its success, he noted that donating Kubernetes to open source and inviting everyone in was critical. It created a neutral ground where rivals could work together on a common infrastructure. We saw in the past how key figures have played catalyst roles, like Linus Torvalds setting in motion the Linux project and then stewarding it, but also knowing when to rely on others' expertise. Lou Gerstner betting IBM's future on an open platform, and all sorts of collaboration happening has helped drive the technology of servers forward. It's striking to consider that the dominant operating systems on servers is free and open source, and that the dominant web server software is open source also. The primary infrastructure management tools, open source, and even the programming languages and frameworks developers use, like Java, Python, Golang, are largely open source. This wasn't preordained. It resulted from decisions by people who believed in the power of sharing and collaboration, often reinforced by pragmatic business reasoning that openness creates bigger markets. The competitive advantage in today's tech industry often comes from not using proprietary technology, but from expertise in using and contributing and making something with open technology. So what will the next decade hold? If history is any guide, new paradigms will emerge, new technologies will come out, but one expects that the collaborative nature of progress will remain. The tech industry has learned that creating de facto standards through open source and shared innovation expands the pie for everyone. Companies will still compete fiercely, but often through differentiating in services or execution rather than hoarding the basic technology. In the end, today's data centers are the result of millions of human hours of collective effort. It's engineers collaborating across time zones, it's organizations aligning on common standards, it's even competitors forming uneasy alliances to solve shared problems. Each generation of server technology stands on the shoulders of the previous one. Linux grew from the ideas of Unix, and cloud computing built on virtualization and the internet, containerization built on decades of operating system research, and the latest AI servers built on all the above. It's a continuum of innovation. For those of us in the tech community, it's a point of pride that cooperation, not just competition, has gotten us this far. All right, that was my long history of servers episode. Thank you so much for listening to the Hands-on IT podcast and making it this far. Until next time, stay curious. And as always, feel free to send in your questions or topics that you love to hear. I'm Landon Miles. This is Hands-on IT. Keep learning, stay curious, and never forget to leave a little room for creativity in your day. Thanks so much for listening.